Welcome to module 24. In this module, we will go over the concept of nitrogen footprint and we will learn about how to calculate nitrogen footprint for consumption. So, where does nitrogen footprint come from? For sustainability assessment, as we are concerned about our impact on ecological systems, nitrogen becomes a very key component. Nitrogen is an important elemental cycle in the biogeochemical cycle realm. The most of the stock of nitrogen is in atmosphere as N2 gas, which is an inert gas and it is unreactive, so it is not useful in that form. However, nitrogen is a very useful component or resource for our existence, including nitrogen in food, nitrogen for energy and also nitrogen in various forms of product and chemicals that we use. The natural nitrogen cycle that is part of our ecological system or earth system includes conversion of unreactive nitrogen to reactive forms such as ammonia and ammonium plus. Ammonia and ammonium plus being in the reactive form can be converted into various products and hence these are very useful for our needs of production. The steps in nitrogen cycle, which is the natural nitrogen cycle, includes the first step as nitrogen fixation. What we call as nitrogen fixation is conversion of inert nitrogen to reactive form of nitrogen. So, which includes N2 gas conversion to ammonia, which can be by the biological process, which includes microbial activity. If you remember, there is also legume nitrogen fixation, and atmospheric lightning is also another process that converts the inert nitrogen into active or reactive form. The next important step in the natural nitrogen cycle is ammonification. What happens in ammonification is that we convert organic nitrogen, which may be present in the ecological system, to ammonium 4 plus, which is the form that is assimilated by plants and other organisms. Assimilation of nitrogen by plants in the natural process is what leads to the generation of biomass, eventually giving us various feedstock for production. The next step in the natural nitrogen cycle is nitrification. Nitrification involves conversion of ammonia to ammonium or ammonium to nitrate via the rate limiting step of nitrite. So, in this reaction we have ammonium or ammonia that is converted to nitrate. Nitrate is the most movable part of the nitrogen cycle and it is the most readily taken up by the plants. Another thing is nitrate is also when it is going to the ecological system, it may also cause pollution. The last step, which is the closing of the natural nitrogen cycle, is what is called as denitrification. Denitrification is very analogous to recycling or conversion of the waste nitrogen into the inert form. So, here the process happens to close the nitrogen cycle by converting nitrate into N2 gas. However, this is not an 100% efficient process because in that process N2 also produces N2O, which is a very potent greenhouse gas. Hence, you can see that the natural nitrogen cycle in its various forms is definitely providing the resources for consumption by humans in terms of biomass and other activities, but in the closing of the nitrogen cycle we are also producing the N2O gas. So, the question is, of course, this is all about how the natural nitrogen cycle happens. So, the question is that how does it relate to the sustainability of human activities or sustainability of human production that we are concerned about in terms of design. So, let us look at the anthropogenic nitrogen cycle. Of course, nitrogen, carbon and water cycle have existed on the earth system for millions of years. But as the human activities have interfered with the natural cycles, we have changed or perturbed these cycles in certain ways. So, here you can see the square box or the rectangular boxes in blue and yellow. So, the blue and yellow forms are actually showing how humans are dependent on the nitrogen cycle, or human activities are interfering with the natural nitrogen cycle. The first one is the industrial fixation. Industrial fixation happens by very famous Haber-Bosch process, where we convert the inert nitrogen into active nitrogen form of ammonia. Now, here this is a very important process because that provides different products that can be converted into useful commodities. For example, we take that active nitrogen and convert it into explosives, plastics and synthetics. It also goes into fertilizers. So, then the fertilizers, when it is used to expedite or increase the production of biomass or crops, that is going into the animal and human food consumption. All of this is actually also going from the useful product that is made into animal and human food. After consumption, it goes into sewage disposal or into the active form as such as ammonium plus, and that goes into nitrite and nitrate. So, you can see that because of the increasing demand of nitrogen as an active resource, we are increasing the rate of conversion of inert nitrogen to active nitrogen. Of course, we know that this has been happening for millions of years. So, ecological systems were in kind of a balance, but now that we have expedited that fixation by more and more legume plantation, more and more industrial fixation, and also more and more energy formation by combustion, which converts the atmospheric nitrogen into NOx, we are perturbing this natural nitrogen cycle. And since we know that lot of these reactive nitrogens such as ammonium plus nitrate has negative ecological impact of eutrophication and other things, or also the greenhouse gas potency of N2O, we know that our activities are dependent on this nitrogen cycle, and they are also causing the negative damage on the ecological system. Hence, it is very important to define a metric that accounts for this impact of human activities on the natural nitrogen cycle, which we term as the nitrogen footprint. Of course, it is not that it is bad to convert the inert nitrogen to active nitrogen, because of we need those resources. So, we cannot really, and that is also happening naturally, but what is the issue is that the rate is very exponential. So, you can see from 1900 to 1975, the industrial nitrogen fertilizer conversion of nitrogen is shot up by 75% or by 50%, from 25% to 75%, and of course, beyond it, it has been even more. Now, we are using more and more plastics and synthetics and textile, which have some form of nitrogen embedded into it. That is why we are becoming more and more dependent on ruining this nitrogen cycle. So, what is nitrogen footprint? In a sense, now that we want to account for our impact on this natural nitrogen cycle and identify ways to reduce that impact, we propose a metric called nitrogen footprint. Of course, we care about nitrogen because it is essential for several products like food, fibers, synthetics, plastic, and the nitrogen loss to the environment has negative impacts like eutrophication. Nitric oxide also has impact on the photochemical smog formation. It also affects ozone in the lower atmosphere, and that has a detrimental impact on human health and ecosystem. The acid rain is also known to be a very important impact, where nitric acid reacts with the sulfuric acid. And lastly, N2O is a global warming potential gas with 290 times more GWP than carbon dioxide. So, how do we measure the nitrogen impact? So, the measure for nitrogen impact is reactive nitrogen, because of course, the inert nitrogen or nitrogen embedded in product is not the one that is causing the negative impact. So, what we do is we account for the reactive nitrogen as ammonia and 2 amines are the resources, and the negative impact occurs due to the reactive nitrogen in various part of ecosystems. So, how do we define nitrogen footprint? It defines nitrogen footprint as total reactive nitrogen lost to the environment due to resource consumption in total NR units or reactive nitrogen units. This nitrogen print project is a project that's launched in United States, and this website gives a very easy to follow nitrogen footprint calculator. We will look towards the theory of this nitrogen footprint calculation in this module and also do a simple example. So, let us look at the two components for calculation of nitrogen footprint. We will only look into the food and energy footprint calculation or nitrogen footprint calculation. So, food, because food forms an important component, food consumption and food production both has an impact on nitrogen footprint. Similarly, energy consumption, because energy leads to some of the NOx formation and causes the loss of reactive nitrogen to the atmosphere. So, here there are two approaches. So, for food there are two components in nitrogen footprint calculation. One is the food consumption and one is the food production. For energy we have the process scale approach, where we look into the use phase fuel and energy consumption and the emissions due to the combustion. For the upstream scale, we can use the input output based approach to look at all the NOx emissions in all the sectors and then quantifying an emissions nitrogen emissions intensity for that. So, let us look at the nitrogen footprint calculation for food consumption. In food consumption, all food consumed eventually ends up in environment as waste. So, it contributes equal amount of nitrogen footprint. So, assumption here is that whatever we are consuming eventually in some process form is wasted through the sewage, and therefore, whatever is the nitrogen content of the food, that is the estimated and the waste generated before consumption is subtracted. So, whatever you consume and we calculate the nitrogen content of that food, and that is considered as the reactive nitrogen that is lost to the environment because of that food being consumed. Anything that is before the waste is subtracted from that particular component. Food production. In food production we take more of a life cycle approach. So, it takes a process scale viewpoint in the sense that we want to understand what are all the steps in that food production and where are all the nitrogen or the reactive nitrogen losses happening in the system. So, for example, it captures the nitrogen footprint or nitrogen losses at each stage of production for all types of food considered and calculates a virtual nitrogen factor. So, remember we talked about virtual water. Virtual water was more about what is the amount of water that is required to support that production. Here virtual nitrogen is also something similar, that is considered the nitrogen that is required to support that production, but instead of being used, it is being lost to the environment, because the way nitrogen footprint is being defined is the reactive nitrogen lost to the environment. So, here what we are going to do, we are not going to just say how much is the input of the nitrogen, but we are going to account for how much is the nitrogen loss at each step, so that we know what is the reactive nitrogen that is going to the ecosystem or environment because of that production step. You can then use this virtual nitrogen factor to get total nitrogen footprint for the production or food being consumed. And it is called virtual nitrogen factor, since it is not the actual nitrogen content of the food being consumed, but supporting nitrogen to produce food. Again, when we are thinking about the supporting nitrogen, remember that it is not the input, but it is the nitrogen being lost to the environment in the reactive nitrogen form. So, here so to avoid confusion, remember we have talked about processing energy when we were talking about the thermodynamic metrics of efficiency and energy return of investment. We were talking about virtual water, where you are looking at how much is the water input. So, it is not the water loss, but the water input, and then you are calculating the increased virtual water at each step because the product fraction is changing. Here we are not talking about the consumed, but here we are talking about the nitrogen being lost, but still we consider that as the supporting nitrogen, because that is being, without that loss the production chain does not happen. So, here is a pictorial example, a pictorial representation that is taken from a published article by Alison Leach on the nitrogen footprint. So, you can see that the figure A on the top is showing the nitrogen flow in the corn production process, and we are starting with 100 units of new nitrogen. So, let us say we have 100 units of new nitrogen and we are applying to the crop nitrogen. because there is some efficiency of uptake of the nitrogen, we can see that 22 units of nitrogen is being lost and only 86 units of nitrogen is being assimilated in that product in that stage. Then when you go to the next stage, we have 65 units of nitrogen that is being lost and about 14 that is actually the crop processing waste, and that is the unit being lost. And you can keep going and you will see that at each stage we have some nitrogen being lost at the stage. So, the virtual nitrogen can then be calculated as the total nitrogen lost per kg nitrogen of output, which is our 42 units of output. Similarly, in the beef production process, you can see that here we have 100 units of nitrogen that is being applied, but in the next stage we are wasting about 24 units, and similarly at each stage there is certain efficiency of utilization. So, in this way you can also calculate. So, here of course, the virtual nitrogen we can calculate as the NR or reactive nitrogen being lost in the whole production chain. And of course, you will calculate it as per kg nitrogen output of the product. Okay. And for this one, you can also calculate something that we call as nitrogen use efficiency, which will be the total output of the product or nitrogen in the product by total input of nitrogen. So, whatever the useful input of nitrogen that has been put up. So, these are some values for virtual nitrogen that has been calculated, and you can see for lot of animal products such as poultry and milk, we have a really high. So, this means that your amount of nitrogen lost to environment is 5.6 kg nitrogen per kg nitrogen in milk product. Okay. And you can see that your beef is really high and your other kind of like poultry and fish and seafood have lower nitrogen footprint. If you look into the vegetable products, lot of the supply chain or the production chain of vegetable production is very inefficient. Therefore, we have a very high virtual nitrogen factor for vegetables, which is 10.6, and then we have starchy roots, legumes and grains. So, you can see that all of that has a very low nitrogen footprint because we do not lose that much nitrogen in the whole production, but vegetables has a really high virtual nitrogen factor. So, now let us see how we calculate the nitrogen footprint for an individual consumption. So, here the equation is very straightforward. We have FP individual, which is the individual nitrogen footprint that we want to calculate. Let us say we want to calculate for an electricity use, it can also be for food consumption. We calculate the average per capita footprint for a country. So, we can know how much is the total lost in the country and what is the total population of the country. So, we can get an average per capita footprint, and then we can take the share of individual consumption of electricity in that particular country. So, for example, EU in individual is saying what is the individual electricity use. You can also say that it is the individual food consumption, and then that is divided by the average per capita electricity use in that country. So, this will give you what is the relative contribution of an individual over the average. So, for example, if this value is greater than 1, which means that the individual consumption is much higher, greater than 1 or higher above average in that particular country, and therefore, your nitrogen footprint for that individual related to electricity consumption will be higher than the average footprint consumption or average footprint of electricity use for that country. Similarly, if it is less than 1, which means that the individual is contributing lower to the average footprint or nitrogen footprint in that particular country. Of course, this equation we can use for any kind of footprint scaling, but here I am demonstrating it in terms of the nitrogen footprint. We can do this equation for each category. So, we can do it for food consumption, we can do it for energy consumption, we can also follow the same equation for let us say vegetable consumption. So, depending on each category, you will be able to calculate the average footprint of the country related to that particular product, and then you can calculate the share of the individual, or whether that individual contribution is higher or lower than the average contribution to that component. So, using this background equation, we can, when you are putting in data for individual consumption, we can get the footprint for that particular component. So, let us look at the components of food nitrogen footprint, and this is just the demonstration of the equation that we just saw. So, here if you look at the A component, it is average per capita nitrogen consumption footprint. So, remember that in food we are saying that whatever the nitrogen content of the food is, that is that is being lost to the environment is the nitrogen footprint of that food. So, here what we are doing is, let us say FAO proteins, which is the Food and Agricultural Organization of the United Nations, it is telling the what is the protein supply data by food type. So, whatever the food type is, how much is the protein content, and then we multiply by the 16% nitrogen in protein. So, that is the nitrogen content. So, this first will give us how much is the nitrogen content in each type of food. Then we subtract the food waste. So, let us say not all the food that is being supplied is being consumed. So, it is being just lost and not being consumed. So, that amount of nitrogen we are subtracting. Whatever we get is the average per capita food consumption nitrogen footprint, because whatever the nitrogen content of the food is, what is our nitrogen footprint, because we assume that all the nitrogen that is contained in that food item is after consumption is being lost to the environment. Okay. Then we calculate the average per capita food production nitrogen footprint. This means that what is the nitrogen footprint that is associated by the production of that food. So, here what we do is that we have the average per capita food consumption. So, this is the amount that is being consumed, and we multiply it by the virtual nitrogen factor. So, your virtual nitrogen factor will tell, let us say we have this as kg nitrogen, then this will be kg nitrogen per kg nitrogen, and that will give us the total nitrogen that is lost in production of this much amount of food that is being consumed. So, that gives us the average per capita food production nitrogen footprint, and when you add these two components, what we are getting is the average per capita food nitrogen footprint. So, that is the food nitrogen footprint. So, let us say we are making grains, then we will calculate the nitrogen content of the grain, which will have the being consumed and lost to the environment, and we will also calculate the virtual nitrogen for the grain production, which is the food production support. So, that is giving us average per capita food nitrogen footprint. The next one is the individual's food consumption by food weight, and then average per capita food consumption by food weight. So, when you take that ratio, that will tell how much is the individual contribution into that, and when you multiply those terms, you will get the individual's food nitrogen footprint. So, that is the equation that we just saw, and this is how all the components of food consumption is actually included into calculation of nitrogen footprint. So, in summary, if you remember, whenever you have to calculate the nitrogen footprint of an individual for food consumption, we first calculate the average per capita food consumption nitrogen footprint, which is the amount of nitrogen that is contained in that food item, plus we calculate the average per capita food production nitrogen footprint, which is the total amount of that food multiplied by the virtual nitrogen factor. And remember that to calculate the virtual nitrogen factor, we have to take a life cycle cradle to gate approach, so that from beginning where we are putting in the fresh nitrogen to all the way to the final product of that component, we are calculating the nitrogen lost at each step. So, once you add those, you have the average per capita food nitrogen footprint from both consumption and production, and then we take the ratio by looking at what is the individual's contribution to the average per capita food consumption in that country. With that, we get the individual's food nitrogen footprint. The next is the components of energy nitrogen footprint. It is again very similar. The only difference here is that when we are looking at the energy nitrogen footprint, we do not have the virtual nitrogen, but the emission factor. And by emission factor, because whenever you are combusting the energy sources, you are generating NOx from the reaction. So here we calculate as the average energy consumption data by sector and type, whatever is the amount of energy, and then we multiply by the emission factor, and that will give us average per capita bottom up energy nitrogen footprint. By sector, we mean that each of the sectors or each of the industry are combusting some amount of fuel, and that fuel is contributing to the nitrogen footprint by emitting emissions into air, and that is why we multiply by the emission factor. So, it could be the kg N2O or NOx being emitted for per liter of, let us say, gasoline. Okay. So, whatever the fuel, you will be able to calculate the emission factor, and you can multiply by the average energy consumption in each of the industry to get the average per capita bottom up energy nitrogen footprint. When we say bottom up, that means that what we are calculating is the actual combustion of the fuel that is leading to the nitrogen footprint. Again, pay attention that here again we are looking at the nitrogen being lost to the environment. In the previous case, for the food, the nitrogen was being lost to the soil or the water. Here the nitrogen is being lost to the atmosphere or the air by the combustion process. Then we multiply the individual's energy consumption and we take the emission factor, and of course we take the ratio for the individual's energy consumption to average per capita energy consumption, and when you multiply it by the average per capita bottom up energy nitrogen footprint, this whole thing will give us the individual nitrogen footprint for energy consumption and the bottom up. There is also the average per capita top down nitrogen footprint, that is basically the national nitrogen emissions by sector, where we are not looking at the actual fuel combustion, but how much was the nitrogen emissions reported by each industry, and then we divide it by the country population. We subtract the average per capita bottom up because we do not want to do the double counting. So, anything that was already accounted by the fuel combustion, we have subtracted it. So, that will give us average per capita top down energy nitrogen footprint, which is also the nitrogen emissions that are not directly reported as the energy combustion, but other sources. Once you add these average per capita bottom up energy nitrogen footprint and average per capita top down energy nitrogen footprint, you get the average per capita energy nitrogen footprint, and when you multiply it by the ratio of individuals' energy consumption with respect to the average per capita energy consumption in the nation, you will be able to calculate the individual's energy nitrogen footprint. So, here in this box, what we have demonstrated is how to calculate the individual's energy nitrogen footprint. But if you go back to the basic definition, all you need to know is how much is the consumption or the fuel being consumed and how it can be used to calculate the nitrogen emissions to the air using the nitrogen emission factor, and that will give us the nitrogen footprint of the fuel or of the particular activity. So, here just a review of that. What are the components included in bottom up energy nitrogen footprint? For the bottom up energy, we have housing has electricity and natural gas, and we can use the average emission factor of nitrogen to get the nitrogen footprint associated with electricity consumption and natural gas. For transportation, you can use either plane, personal car or public transit, and for each of that you can calculate the emission factor and multiply by the distance that is traveled to actually know the nitrogen footprint of that particular amount of travel. Similarly, if you are traveling in a personal car, you can know the average emission factor per miles travel or per kilometer travel and multiply by the kilometers that you are traveling to get the nitrogen footprint of your personal car travel. So, in the energy footprint, we need to know the actual combustion factor or the emission factor and the consumption that we are doing of that particular energy source. So, now what we will do is we will just look at an example and calculate the nitrogen footprint for these two consumption, and these both of those are actually the food products. There is also, in this example, we are giving the energy that is input to these food production, so that you can also calculate the nitrogen footprint associated with energy consumption to support this food production. So, I will show you the calculation for beef consumption, and then we can do an exercise to calculate for grains composition. Okay, let's look at the beef consumption. So, for beef consumption, we are given the consumption in terms of amount and also the nitrogen content of the food product. So, remember that for food nitrogen footprint, we need to account for the nitrogen footprint due to consumption plus the nitrogen footprint due to upstream losses. So, the nitrogen footprint due to consumption means that what is the nitrogen content of the food that we are consuming. So, here we have 10 kgs of food that or beef we are consuming, and the nitrogen content is given as gram per 100 grams. So, we have 15.8 grams in 100 grams of beef, which means that about 15.8 by 100 into 1000, this is gram per kg, and we can convert it into kgs. So, that will be, this is the amount of kg nitrogen per kg of beef being consumed, and the nitrogen footprint due to the upstream losses will be 10 kg, and our virtual nitrogen factor is 8.5. So, we multiply by 8.5, that is the kg nitrogen, that is because of the food production. So, that is the food nitrogen footprint. In this case, we are also given the energy associated with production, and we have 1 kilowatt hour of electricity consumed for per kg. So, we can add the nitrogen footprint due to energy consumption as well. And that we can add as, we have 1 kilowatt hour per kg. So, we have 1 times 10 kilowatt hour of electricity, and the emission factor is given as 5.10 to the power 5 kg nitrogen. So, we have multiplied by 5 10 to the power minus 5 kg nitrogen per kilowatt hour. So, now we have all of them in the same unit. So, our total nitrogen here, or the food nitrogen footprint for this case, will be about 86.6 kg nitrogen. So, that is your nitrogen footprint for beef consumption. So, just to reiterate, when you are calculating the food nitrogen footprint, you want to include the nitrogen footprint due to consumption, which is the actual amount of nitrogen embedded in the product, nitrogen footprint due to upstream losses, which is to support the production. Here you multiply the total consumed with the virtual natural factor. Virtual nitrogen factor is calculated separately, and then if you know what is the amount of energy that is being taken or given to support that production, you also calculate the nitrogen footprint, which is the nitrogen emissions due to the energy consumption to support that production. So, let us take 30 seconds and calculate the nitrogen footprint for grains consumption. Alright, let us look at the grains consumption. So, for grains consumption again our nitrogen footprint will be the nitrogen content in product or nitrogen due to the consumption, which is assumed to be lost to the environment. Then we have nitrogen losses upstream or due to the virtual nitrogen factor. And then the nitrogen due to energy consumption. So, here our nitrogen content in product, we have 5 kgs of grain, 2.54 grams per 100 grams. So, in 1 kg it is 2.454 by, and then we divide by 1000 to get the kg nitrogen. And nitrogen released in production, we have 5 kgs and the virtual nitrogen factor is very less, it is 1.4. So, we have 5 into 1.4 kg nitrogen, and we have 0.2 kilowatt hour of electricity per kg. So, 5.2 into 5 and multiplied by the emission factor of 5 into 10 to the power minus 5 kg nitrogen. So, that value will come out to be approximately 7.127 kg nitrogen. So, you can see that the nitrogen losses to the environment or the nitrogen footprint of grain consumption is only about 7.125 kg nitrogen, but the nitrogen consumption or nitrogen content for the beef was about 86 for 10 kgs. So, with that we can infer that the consumption of beef here is really detrimental to the environment in terms of nitrogen impact as compared to the grain, and that is one of the data that supports why some of the vegetarian foods like grain and vegetables which have a lower virtual nitrogen may be more environmental friendly as compared to the meat consumption. Of course, you need to also account for other aspects such as the effect on the water quality and the effect on the water pollution, water footprint, carbon footprint, and thus because and also the land use such as ecological footprint. So, just looking at one single metric, we cannot make a univariate decision about which product is more environmentally friendly. Of course, some product may be much better in one dimension, but worse in the other dimension. So, you have to really take a more holistic picture. However, when we take the nitrogen footprint case, in this case we can see that grain consumption is more environmental friendly in terms of nitrogen footprint. So, going forward, what nitrogen footprint does, it is a measure of stress on nitrogen cycle or the ecological system in terms of reactive nitrogen, which causes the negative consequences in the environment due to the reactive nitrogen species. To calculate nitrogen footprint, you need to consider all the upstream reactive nitrogen utilization and also the nitrogen content of the product that will be eventually released to the environment. And virtual nitrogen values, which are mostly the supply chain or the total nitrogen losses in each of the life cycle stage for each product, are calculated using the life cycle approach. For a lot of the products, these values are available in the literature, but these needs to be calculated specific to every supply chain or the region, and therefore, we need that additional data and transparency on the supply chain. Hence, it is said that food supply chain is very critical because we do not know a lot of the nitrogen losses along that food supply chain in current scenario. With that, thank you for coming to this module. In the next module, we will start talking about ecosystem services. We have been talking about how we are affecting environment using the footprint such as ecological footprint, water footprint, carbon footprint and nitrogen footprint. Now, we will start looking at how does ecosystem support the production, and what is the dependence of different human activities and how on the ecological resources or ecosystem services, and how do we account for them in our assessment.